So now we're just going to do a couple of examples applying the rules that we've seen so far, or at least some of them. So the first one, and also I've written these in a couple of different forms because I just want to get you used to using the different terms and notations. So the first one is to differentiate negative 3x minus 2 over 5x cubed plus the square root of, sorry, not the square root, the fifth root of 32x to the seventh and minus e to the pi. So we want to differentiate this function. I mean, strictly speaking, I should say differentiate with respect to x. But since x is the variable, I think that is implied if you don't say it, if that's the only variable. So anyway, let's find the derivative of that function. So first thing I want to do actually is I want to rewrite this in the form. I want to make sure I rewrite everything here as a power, so because then I can apply the rules more cleanly. So this is going to be negative 3x minus, this will be 2/5 x to the negative 3. And then this function here, sorry, not function, this expression, the fifth root of 32x to the seventh, I can rewrite that as the fifth root of 32 times the fifth root of x to the seventh. But what that's going to give us, the fifth root of 32 is just 2, and the fifth root of x to the seventh is x to the 7 over 5. And then here we have e to the pi. And by the way, before I do before I finish the problem, I encourage you to stop the VHS tape that you're watching this on, and then just work the solution out yourself. But otherwise, you can either just watch it or you can try to solve it yourself and then check the solution. I think you'll get more out of it if you of each of these problems if you stop and try to solve it yourself. So here we have the derivative of negative 3x is just going to be negative 3. Recall that if I view this as x to the 1, this is just an application of the power rule, but I had mentioned earlier that it's useful to remember that the derivative of ax for any constant a is just a. So you can remember that. For the next term, we have 2/5 times, this is going to be negative 3 x to the negative 3 minus 1 is negative 4. A very common mistake that people make when dealing with negative exponents is they try to use something like negative 2 there. And they don't realize that the power rule is quite literally what it says, is you subtract 1 from the exponent. That means that if your exponent is negative 95, you don't go to negative 94, you go to negative 96. You're actually subtracting the number positive 1 from whatever the exponent is, positive or negative. So this is now going to be plus 2 times 7/5 x to the 7/5 minus 1, or 7/5 minus 5/5 is going to be 2/5. And then we have, many people assume that the rule here is that e to the anything, its derivative is just e to the anything. That's not correct. The next thing people often assume is they say, well, e is a letter, so it must work sort of like x, and therefore this must be pi e to the pi minus 1. But that's also not correct. The thing to recognize is that e to the pi is just a constant. It's a very complicated number, but it's still just a number. It's a number. I could have, the function, I could have the horizontal line up here, y equals e to the pi, and we'd see it's still a horizontal line. Its slope is 0 every place. So this is just 0. And finally we can clean this up a little bit. This is going to be 3/5 plus, that's going to be 6/5 x to the negative 4. Actually, let's write this in positive exponent form. So that's going to be 6/5 over x to the 4. So let's put that there. And then this is going to be 14/5 x to the 2/5. So that is the derivative of that function. All right, so for the next problem, let's let y equal e to the x tan x, and we'll find dy over dx. So this is, by the way, just another symbol for the derivative of y, where y is a function of x. So this symbol, find dy over dx, just means find the derivative of the given function where we've expressed y as a function of x. So here we can use the product rule, where that's f and that's g. So go ahead and try to find that derivative. Dy over dx is going to be fg prime, so that's e to the x times secant squared x, and then plus f prime of g e to the x is its own derivative, so we can write e to the x there, and tan x. So, or we could just write e to the x secant squared x plus tangent of x. By the way, I'll just put these in here. So that's f, that's g prime, that's f prime, which happens to be the same as f, and that's g. So there we go. Here we have a couple of problems that are a little bit more abstract. So let's suppose that all we know about f and g is that f of 2 is equal to 3, f prime of 2 is equal to 5, g of 2 is 7, and g prime of 2 is 9. So if h of x is the product of these two functions, let's find h prime of 2. Well, the thing to realize is that we're just applying the product rule here. So we know that h prime of x is equal to f of x g prime of x plus f prime of x g of x. So that means that h prime of 2 is equal to f of 2 g prime of 2 plus f prime of 2 g of 2. And that's going to equal, let's see, f of 2 is 3, g prime of 2 is 9, f prime of 2 is 5, and g of 2 is 7. So that's going to equal 3 times 9 is 27, 5 times 7 is 35, 27 and 35 is, if I'm doing my arithmetic correctly, that's going to be 62. So that's the answer. And keep in mind that, even though we've been doing things where we're finding new functions, expressions that involve x, when we're talking about h prime of 2, remember that what we're talking about is for some squiggly line function like that, if this is y equals h of x, what we're talking about here is the slope of the tangent line over the number x equals 2, which means that at the point that's over that corresponds to x equals 2. So it's going to be a number. The slope of a particular line is a particular number. It's not some abstract expression. It's an actual number. So all right, let's do this next problem. So let's suppose that h of x equals x cubed f of x. Let's find h prime of 2. So here, we once again want to apply the product rule. It's just a little bit, the reason it's a little more complicated is in one case I have an actual function, in the other case I have a purely symbolic expression for a function. So h prime of x is going to be, since this is actually just a product of those two functions, this is going to be x cubed times the derivative of x plus the derivative of x cubed, which is 3x squared, and then times f of x. That's how the product rule applies to this expression. Made it a little complicated by putting the f in the position that we usually, it's the second function, it's usually what we call g. I put it there because it doesn't really matter what we call each function, you just have to apply the rule correctly. So here we can now calculate h prime of 2. That's going to be 2 cubed times f prime of 2, and then plus 3 times 2 squared times f of 2. So that's going to be 8 times, let's go up here, f prime of 2 is 5, and then plus 3 times 2 squared is 3 times 4 is 12 times f of 2 is 3. So that gives us 40 plus 12 times 3 is 36. That equals 76.